Engineers at Lockheed once built a spy aircraft many experts believed shouldn't even work. A jet designed to fly faster than missiles, higher than most planes could climb, and survive heat intense enough to destroy ordinary aircraft. Pilots wore astronaut-style pressure suits, engines operated like continuous controlled explosions. Even the fuel doubled as coolant just to keep the aircraft from tearing itself apart. At extreme speed, friction heated the skin to hundreds of degrees, metal expanded mid-flight. Every second pushed technology to its absolute limits. This wasn't some secret experiment or short-term prototype. It flew real reconnaissance missions. For the United States Air Force, operating where interception was nearly impossible. This is the unbelievable engineering story that turned the impossible into reality and redefined the limits of aviation. Welcome to Elite U.S. Millitary, where power, technology, and the real stories behind military innovation come alive. In the late 1950s, the United States had a terrifying problem. The Soviet Union had shot down a U-2 spy plane over Sverdlovsk. The message was clear: slow, high-flying reconnaissance aircraft were now easy prey. But Washington still needed to know what was happening deep inside Soviet territory missile fields. Bomber bases, new radar systems. Satellites were in their infancy and couldn't guarantee timely coverage. The CIA and the Air Force wanted something no one had ever built before: an aircraft that could outrun the very concept of interception. The requirement that eventually produced the Senior 71 wasn't just make it fast. It was more like fly above 80,000 feet higher than any enemy fighter could reliably reach. Cruise at Mach 3 for hours, not just seconds. Cross continents in less time than it took a Meg to climb an arm. Carry cameras and sensors good enough to read license plates from the edge of space. And do all of that every week, not just once for a record book. That set of demands runs straight into some brutal physics. At Mach 3, air friction becomes your primary enemy. The faster you go, the more kinetic energy you're forcing into the boundary layer of air that hugs your skin. That energy turns into heat. Internal fuel lines would cook. Conventional jet engines would choke, overheat, or simply melt. On top of that, there's the problem of thermal expansion. Heat makes materials grow. At Mach 3 cruise, the Senior 71 didn't just get warm, it got longer by several inches. Joints, panels, fuel tanks, windows, even the cockpit frame all had to be designed to survive a jet that was literally changing shape in flight. And remember, this wasn't a one-off stunt. Lockheed Skunk Works wasn't designing for a single run down a speed record course. They had to build a fleet that could take off from bases, accelerate to impossible speed, cross hostile borders repeatedly, collect data, and get home week after week, year after year. They didn't break the laws of physics. They went right up to their edge and built a machine that lived there. The first problem to solve was the airframe itself. Traditional aircraft structures were out of the question. Aluminum would literally creep and fail at the skin temperatures the Senior 71 would see. So Skunk Works turned to a then exotic material, titanium. Titanium is light like aluminum but strong like steel, and it keeps that strength at high temperatures. Perfect in theory. In practice, working with it in the 1960s was a nightmare. The US didn't have a mature titanium supply chain, ironically. Much of the raw ore used for the Blackbird's titanium came from the Soviet Union, routed through front companies, so the people America was building the jet to spy on were partly supplying its metal. Titanium also hates impurities. Standard machine shop tools would contaminate it. Welds had to be done in sealed environments. Early attempts at making parts resulted in cracking, warping, and catastrophic failures. Skunk Works engineers had to invent new tooling, new welding techniques, and new quality controls just to get usable structural components. When they finally put the aircraft together, a new problem surfaced. On the ground, the Senior 71 leaked like a sieve. Up close, a Blackbird wasn't a perfectly smooth sculpture. It was full of tiny gaps, sliding joints, and flexible seals. That was deliberate. Engineers knew that at Mach 3, the whole airframe would heat up and expand. Those gaps would close as the structure grew. If they built it tight on the ground, it would buckle and tear itself apart in the air. That meant at ambient temperatures, the fuel tanks didn't fit tightly. JP7 fuel would seep out of panel lines and joints, dripping onto the ramp. Crews learned to accept puddles under the jet as normal. The Senior 71 didn't fully seal until it was hot from flight. Even the fuel itself was part of the engineering solution. Standard jet fuel would flash into vapor, or even catch fire under the conditions inside the Senior 71 systems. The Blackbird used a special high flash point blend called JP7. It was so stable that you could drop a lit match into a bucket of it and the match would go out. That stability made it safe inside scorching fuel lines and tanks, but it also made JP7 hard to ignite in the engines. The solution? Trethylburana, pyrophoric chemical that explodes on contact with air. The Senior 71 carried small TEB tanks that squirted into the engine to light it off with a violent green flash every time the pilot hit the start sequence or selected afterburner. Now add the windshield. At 80,000 feet and Mach 3. The windscreen could reach over 600 degrees Fahrenheit. Pilots sat inches away from glass as hot as an oven door, protected by a combination of high-temperature materials and advanced, for the era, environmental systems. Their pressure suits had to handle not just thin air, but the possibility that any seal failure would expose them to those temperatures. All of this created a kind of paradox on the ground. The Blackbird was almost fragile, leaky, temperamental, unpleasant to maintain. At speed and altitude, when every normal jet would be dying, the Senior 71 was in its element. The engineering was tuned to a specific, hostile slice of the flight envelope, and accepted that everything before and after would be ugly. It wasn't just about surviving the heat. The next trick was turning the engines into something that behaved less like turbojets and more like controlled explosions riding a shockwave. Look at a picture of the Senior 71 and your eyes are drawn to the huge nacelles hanging off the wings, those long, pointed spikes leading into round inlets. On paper, the J58 is a turbojet. In practice, at Mach 3, it behaves like a hybrid between a turbojet and a ramjet, something no standard fighter engine can do. Here's the problem. As an aircraft accelerates, the air entering the engine inlet is compressed by the shockwave at the front lip. At high Mach, that compression becomes extreme. If you just ram Mach 3 air into a normal compressor, you'll get an engine stall or destruction. You have to slow the airflow down and pre-compress it in a controlled way. The Senior 71 did that with a combination of inlet spikes, bypass doors, and a key piece of machinery called the inlet cone control system. At low speeds, the pointed spike at the front of each nacelle sits forward. Air flows smoothly into the engine, and the J58 behaves mostly like a conventional afterburning turbojet. As the aircraft accelerates through Mach 1, Mach 2 and beyond, that spike slowly moves backward, controlled by a computer that watches Mach number and pressure. Each movement of the spike changes where the shockwave stands in front of the inlet. The goal is to place the main shockwave just ahead of the inlet lip and then trap a series of weaker shockwaves inside the inlet duct. This stair-step pattern reduces the air, speed and temperature to something the compressor can handle while still extracting huge kinetic energy from that incoming flow. At the same time, bypass doors around the nacelle open and close. As speed increases, more of the air can be routed around the turbojet core and directly into the afterburner duct. By Mach 3, as much as 80% of the total thrust isn't coming from the compressor and turbine at all. It's coming from air that never touched the compressor air that was compressed by the inlet geometry and then burned in what is essentially a crude, controllable ramjet section. In other words, the J58 feeds, stabilizes, and starts the flow at low speeds. But at high speeds, the inlet system itself is the engine. The turbojet core keeps spinning, providing some thrust and the mechanical power to run the pumps and systems. But the real work is being done by carefully shaped shocks and ducts that take Mach 3 air and turn it into forward push. Managing this was non-trivial. If the spike moved too far, too fast, the shock could detach and get swallowed by the inlet, causing an unstart, a violent loss of inlet compression that would slam the aircraft sideways and rattle the whole airframe. Pilots described unstarts as feeling like being rear-ended by a truck at altitude. The solution: an automatic control system that could rapidly move spikes and doors to catch the shock again, and pilot procedures to cross-feed air from the healthy engine while the other one recovered. Fuel again played a vital role. JP7 wasn't just sitting in tanks waiting for burners. It was circulated through heat exchangers to soak up waste heat from the engine oil, hydraulic fluid, and even the aircraft's skin before being burned. The Senior 71 literally used its fuel as a heat sink, dumping thermal energy into JP7 and then blasting that heat out the back as thrust. Put all of this together, and you get a system where, at takeoff, the Senior 71 behaves like a heavy, underpowered jet. At subsonic and low supersonic speeds, it's a high-performance afterburning fighter-type engine. At Mach 3, it's fundamentally a flying shockwave stabilized ramjet with a turbojet core along for the ride. To pilots and engineers in the 1960s, that felt like something that should have been illegal. It wasn't. It was just physics pushed so far into a corner that most people never think about it. Have you ever heard of a plane so fast it could outrun missiles? A spy plane that flew so high it touched the edge of space? Meet the SR-71 Blackbird, the undisputed king of speed and stealth, a legend of the Cold War that remains an icon of aviation engineering to this day. It was the 1960s, a time of intense rivalry between the United States and the Soviet Union. The U.S. needed eyes in the sky, a way to gather intelligence without being detected or shot down. The famous U-2 spy plane was good, but it was vulnerable. So the legendary Skunk Works division at Lockheed, led by the brilliant Kelly Johnson, was tasked with creating something impossible, an aircraft that could fly faster than a rifle bullet, at altitudes where the sky turns black. The result was the SR-71. This wasn't just a plane. It was a masterpiece of innovation. Its skin was made of titanium to withstand the insane heat generated by friction at high speeds. We were talking over 600 degrees Fahrenheit. The plane literally leaked fuel on the ground because its panels were designed to expand and seal up only when it reached its blistering operational temperatures in the air. And its performance? Absolutely mind-boggling. The Blackbird could cruise at over Mach 3.3, that's more than 3 times the speed of sound, or over 2,200 miles per hour. It flew at an altitude of over 85,000 feet. At that height, the curvature of the Earth is clearly visible. For pilots, it was like being an astronaut and a pilot at the same time. They even had to wear special pressurized flight suits similar to what astronauts wear. The Blackbird's primary mission was strategic reconnaissance. It was packed with state-of-the-art cameras and sensors that could survey over 100,000 square miles of territory in a single hour. From 85,000 feet, its cameras could capture details as small as a license plate on a car. This gave the United States an incredible intelligence advantage during the Cold War, providing crucial information on military movements and installations without ever entering hostile airspace directly. So, how did it deal with threats? The SR-71's greatest defense was its incredible speed and altitude. If a surface-to-air missile was launched at it, the standard procedure wasn't to evade. It was simply to accelerate. The Blackbird could literally outrun the missile. Over its entire service life, from 1964 to 1998, more than 4,000 missiles were fired at SR-71s. Not a single one was ever shot down. Let that sink in. 0 losses to enemy fire. Even after its retirement, the legacy of the SR-71 lives on. The technology developed for the Blackbird, from its stealth characteristics to its advanced materials and engine design, pushed the boundaries of what was thought possible in aerospace engineering. It paved the way for future stealth aircraft like the F-117 and the B-2 bomber, and its data helped NASA develop spacefaring vehicles. The SR-71 Blackbird was more than just a spy plane. It was a symbol of human ingenuity, a testament to pushing limits, and a silent guardian that watched over the world from the edge of space. It remains one of the most awe-inspiring aircraft ever built, a true black phantom of the skies that continues to capture our imagination. Thanks for watching. If you were as amazed by the SR-71 as I am, hit that like button and subscribe for more stories of incredible engineering. See you in the next one. You've been watching Elite U.S. Millitary. If you want to follow up on the craziest Senior 71 missions ever flown, including the day a Blackbird outran over a dozen missiles in a single sortie, tell us in the comments. Type Blackbird so we know you made it to the end. Make sure you like this video, subscribe to Elite U.S. Millitary, and hit the notification bell so you don't miss our next deep dive from stealth bombers just entering service to Cold War legends that flew so fast and so high they still don't quite seem real.